Hello and welcome. My name is Riku Varis and I'm coming from Tampere University in Finland, and I'm part of the research center Terra, which is the department inside the Tampere University. And today my topic is track geometry errors caused by convex turnout crossties. And I'm doing this research together with my colleague Tommi Rantala. Well, we can start about the background in Finland. So there are more than 5,000 turnouts in the Finnish rail network, and 42% of these are laid on concrete crossties. So most of our turnouts are still in wooden sleepers, but quite many are now in concrete crossties. And several elevation, cant and twist errors have been evaluated in these turnouts, in these concrete turnouts during recent years. And errors are increasing, unfortunately, all the time. So something has to be done. Damping has been obviously the main method for fixing these errors, but during recent years also height adjustment plates have been used between the base plate and the crossties. So these kind of errors has been tried to correct with the height adjustment plates. But any of these methods haven't been effective enough to improve the geometry, and problems have returned quickly after maintenance. So we want to really understand why there is elevation, cant and twist errors, what is the reason for these. And they have just been damping and they have used the adjustment plates, but there hasn't been really understanding what is happening, why we have to use so much damping and why we have to use these adjustment plates. So this project divided the vertical geometry errors in turnouts roughly into three groups. So there is transformations in steel parts. So if there is something wrong with the actual rail or fastening systems, then there is transformations in crossties and transformations underneath the crossties. And this project is, of course, focusing now in the transformations in crossties. Well, the convexity of concrete crossties. In principle, all the concrete crossties are assumed to be completely straight. So when you are casting the concrete sleeper, you assume that it's completely straight, as the casting is. But in reality, the concrete crossties are a little bit convex, and there are several reasons for this convexity. In example, pre-stress structure, which tends to pull the crosstie into convex shapes. So there is more steel in the lower section of the crosstie, and it's pulling the crosstie in convex shape. And then there is creep of crossties, so that's slowly evolving thing in a matter of time, which are increasing the convexity. It could be caused by the bad storaging or something, or in track, but there is creep of crossties in time. And then there is, of course, loading of the trains, but the loading in the track, and it's a tricky one because that can, of course, increase or decrease the convexity depending on the load. So we don't know what it does in the crossties, but it can do both. And according to the Finnish regulations, the vertical deviation, when we are talking about convexity or concavity, the vertical deviation of new crosstie can be maximum 2 millimeters when the length of the crosstie is under 4 meters, and it could be 4 millimeters when the length of the crosstie is over 4 meters. So this is a little bit more tight than the EN standard. The EN standard is more loose to this, but we have these kind of regulations in Finland. Then the measurement. So we want to measure the convexity of the sleeper. and it was defined with the help of tachometer measurements. We used also other measurement methods, but mostly tachometer measurements was used. And the idea was not to find the maximum convexity between the crosstie ends, but to define the height difference between the rail fastenings, and that way understand how this can affect the rail geometry. It's no point of measuring the maximum convexity, because that doesn't affect the real rail geometry. Only the fastenings, the convexity between the fastenings is the kind of the real deal. So we are measuring 1, 2, 3, and 4. The measuring points are in the picture. And all the measurements was done without any train loads. So we want to reveal the natural shape of crossties in track. We want to see how convex it is in its natural shape in track. And the convexity was examined in almost 25 different turnouts. So at least 500 crossties was examined, even more. Then the convexity results. According to results, the convexity is clearly seen in the crossties, concrete crossties, but it differs quite a lot between different turnouts. And the convexity is significant, especially in the long crossties, where the distance between the outer fastenings are more than 3 meters. So naturally, when the crosstie is really short, then the convexity is meaningless, because it's so short, the turnout. So the convexity, it doesn't have enough length to grow or matter anyway. But when it's over 3 meters, then there's really big issues about the convexity. And the typical convexity in long turnout crossties is 2 to 4 millimeters. And here is the picture of few turnouts. So there is a different cities, and there is a turnout number. So there is Karjärvi turnout number 4 and 2, and then there is Ylöjärvi turnout number 2. And then there is a number of sleepers or crossties in the different colors are the number of the crossties. And as you can see, that they are all approximately 3.5 to 4 meters, the length of the crossties in those pictures. And in Finland, that kind of crosstie is underneath the crossing nose. So underneath the crossing nose, the length of the crosstie is approximately 4 meters. So these sleepers are a little bit before the crossing nose, and the convexity before the crossing nose is already can be 4 millimeters. And the loading can increase the convexity of the crossties during life cycle if the contact between the crosstie and the ballast is insufficient. So if there is bad contact between the crosstie and the ballast, and it's in the air, you can see that the crosstie is in the air, the crosstie ends are in the air. It can really increase the convexity, and it can grow even 8 or even 10 millimeters the convexity. And that means that if the convexity is that much, we believe that there will be some kind of cracks already in the sleeper when the convexity has increased that much. In these few examples there in Ylöjärvi and Karjärvi. And then convexity can also decrease, especially underneath the crossing nose, where there is really big, large impact forces in the middle of the crossties. So there is impact forces right in the middle of the long crossties, and that is kind of beating the crosstie and forcing that to be straight. And that also can eventually lead to cracking of crosstie. But the problem is that when the convexity is increasing, then the cracks are evolving in top of the sleeper, of course. of the cross ties, so we can see the cracks in top layer of the cross tie. But when the convexity is decreasing and the structure is straightening out, then the cracks are evolving in the bottom layer of the cross tie, and we cannot see them. So we cannot know is it in bad shape, the cross tie. And if it seems completely straight, I can say that nobody cares if the cross tie is completely straight. Nobody says that there could be cracks already when it's straight. Then, how the convex shape affects to the cant values. So the cross tie can be orientated so that the cant values of the straight route is always 0, and that will prioritize the more important route. As in the picture, you can see the green one and the red one. They are really convex mirrors or convex cross ties, but the cant values of the straight route is 0, so there is no cant in the straight route. But when you are orientating cross ties like that, you can see that the cant values of the diverging route could be 6 millimeters. So it's really increasing this kind of orientation is really increasing the cant values in the diverging route. And the long cross ties tends to tilt towards to the route which is more used, and normally that more used side is the straight route. So they are tilting, and that's a problem because in the heel of the turnout short cross ties, the normal cross ties, are settling evenly, so they are just evenly settling down. But the last long cross ties in front of them, they are tilting, so they are kind of evolving. They are evolving cant values, but short turnouts are short cross ties are. The cant values could be 0, but next to them there is long cross ties where the cant values is not close to the 0. So this creates really big twist errors in the transition areas between the long cross ties and the short ones. And convexity of long cross ties are increasing the cant values in tilting situation compared to the straight cross ties. So if the cross tie would be completely straight, the tilting wouldn't be so hazard, but now when it's cant, when there is a convex shape, the tilting is even worse. Then the consideration of convexity during damping. As you can imagine, the actual shape of the cross tie have to be considered in damping. So you have to know the actual shape of the cross ties. We have believed that the cross ties are completely straight, but now when we know that they are not completely straight, you have to know that when you are damping. And in practice, this means that it's impossible to align both routes completely horizontal with convex cross ties. So somewhere, the result is that there is somewhere cant after the damping. If you just use normal fastenings, the result is that cant is somewhere. And the adaptation of convexity during damping is almost impossible. So I mean that you try to remove the convexity in the sleeper. That's not good because probably that leads only to larger problems if you accidentally crack the cross tie. So you can try to remove the convexity in the sleeper, but that will just crack the sleeper. And the cant, which is created by the convexity, so in this leads to that the cant which is created by the convexity should be left intentionally to the diverging route without even try to force it completely horizontal. So the speed limits normally the speed limit in the diverging route is lower than the straight route, and then the maintenance level of the diverging route is lower, so it can take more cant values than the straight route. So it's the same cant value is not error in the diverging route because of the lower maintenance limit. So you should leave it intentionally in the diverging route. But this is problem in track junctions, where the cant of two consecutive turnouts are in opposite direction. Of course, the diverging routes are facing in the middle, and the cant values of the convexity is in opposite direction, so it's a problem. And it creates really big twist errors in the diverging route. So in junctions, the cant values must be left in the straight route. There is no other way. Or of course you can use adjustment plates underneath the rail, so to leave all the rails in the same horizontal plane. But still the crossties are convex in the straight route. So in summary, generally long turnout crossties are not completely straight, as you would think. And most turnout crossties are a little bit convex, which means that the center part of the crosstie is higher compared to the ends. And the convexity is typically 2 to 4 millimeters. And loadings in the track can change that convexity. And underneath the crossing nose, the impact load can straighten the crossties or even turn it to concave. But convexity can also grow, and the measurement result revealed that the convexity can be even 10 millimeters if the contact between the ballast and the crosstie is not insufficient. And because of the convexity, straight route and diverging route cannot be completely horizontal at the same time. So you should understand that. And during damping, the cant should be left intentionally in the diverging side, where the speed limit is not so high. But the convexity shouldn't be removed by force, because that will only crack the crosstie, leaving even bigger problems. So you should leave that convexity in the sleeper and try to use it, the cant values in the diverging route, or use height adjustment plates to kind of compensate this convexity. But you shouldn't try to remove that convexity in the sleeper, because that will crack the sleeper. Thank you.